The next question on chemical kinetics is from Lindemann mechanism for unimolecular decomposition of a molecule. So you are asked to determine what will happen for a Lindemann mechanism at different pressures, whether it is high pressure or low pressure, etc. So to determine this, we can, even though it is a very simple problem, let us try to go to the mechanism of Lindemann molecular reactions. The reaction mechanism is like this: a molecule of a molecule, it collides with another a molecule, and it will give an energized molecule plus another a molecule. The forward rate constant is K1, and this reaction can be reversible. It is not like a reversible or equilibrium reaction, it's a reversible reaction. So the backward rate constant is written as K inverse 1, meaning to say A star and A can combine together or collide together again to form the de-energized molecules. And the next step is the rate determining step, which is given by K2, so that will be giving you the products. So this is the RDS, meaning to say the rate determining step. And since it is a rate determining step, the rate can be given as rate will be equal to K2 into A star. So our problem is to determine the concentration of A star. Generally, we are using steady state approximation SSA to determine the concentration of A star. So steady state approximation will be the change of concentration of A star with respect to time. A star will be equal to 0. So once you apply the steady state approximation, you will get the final equation, final form for the A star, and the rate will be equal to K2 into, and A star will be K1 into A square divided by K2 plus K inverse 1 into A. So this is your equation, and now let us see what will happen at low pressure. So here to find at low pressure what will happen. At low pressure, since you know the equation, the denominator is K inverse 1A and K2. At low pressure, K inverse 1A will be much less than K2, so that you can eliminate that part, so that your rate will be equal to K2 into K1 into A square and divided by K2. So if you approximate this to another constant, you can see this is A square, so that this is a second order reaction. Now that was under condition of low pressure. Now at high pressure what will happen? At high pressure, your K inverse 1A is going to be much greater than K2, so that you can eliminate K2, so that rate will be equal to K2 into K1 A square divided by K2 can be eliminated, so this will be K inverse 1 into A. So this is A square and this is A, so that this can be approximated to another constant. Let us call it as a K dash into A, and this is a first order reaction. Meaning to say, a Lindemann mechanism will be second order at low pressure and first order at high pressure. Now, since you check the options again, you can see it follows second order kinetics at high pressure, that is not the one. It follows second order kinetics at low pressure. So your right option is 2.